motions and sound effects and everything that this is an exponential graph. What is a model? What is a model? Okay, it could be something you build out of plastic and you paint, of a car or a plane or a boat. What else is a model? It's a way to explain something. You can have a computer model. A graph can be a model of how a population behaves. So this is called the exponential growth model. Exponential, just like that exponential graph we did. And hey, look at that. There's that curve we just described. Whoop! 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 So much fun. I had to do it again. The exponential growth model is a way of describing a population that is growing at a steady rate and who's growing rapidly and that expands tremendously after just a few generations. We're going to talk about two different growth models today, exponential and logistic. And for each of them, I want you to very carefully look for the word assume. Okay? Because in each of them, there is some underlying assumption. And in the exponential growth model, here's the assumption. It assumes that no matter how big this population gets, the birth rate doesn't change, and the death rate doesn't change. So if that happens, guess what? Right off the charts. Sometimes this is called J-curve growth. Can you see why it might be called J-curve growth? Because what does that curve look like? A J. It's so much fun, isn't it? So, has anybody here ever raised mice? Anybody ever have pet mice? Cute little pet mice, little white mice, little brown mice. I used to have some mice in my classroom. They died. I haven't gotten any back. When I was in college, my friend Sally had mice. They were cute. She had 3 mice. And she had 2 tanks, 2 aquaria. And she was pretty sure she had 2 females and 1 male. Now, I do not know how to tell sex on mice. I know how to sex rabbits. But mice, and they're tiny. My God, how do you see it? I don't know. I mean, once they're old enough, the males have pretty obvious testicles. But prior to that point, it's tough to tell. So she had these 3 little young mice. She figured she had 2 females and a male. So she had the 2 females in 1 tank. She had the 1 male in the other tank. Do you see where this is going? Oops! She misidentified one of the females. It was a male. How did she find out? Because one of the females had like 7 babies. Ooh. Oh, it's going to get a whole lot worse. That was paused. So in nature, we don't usually see this because typically we see this in a short burst maybe, but then there's a crash. So I'm going to invite you all to stand up and we'll do some sound effects and motions once again. So anytime that we see J-curve growth in the wild, what tends to follow is a crash. We tend to see a population crash. So let's think about a barn cat colony, because their feral cat colonies are a classic example here. You get breeding. You go from 1 or 2 feral cats to hundreds of feral cats. What do you start to see? They leave the area. They migrate outward. They die. You start to see disease epidemics. And they actually can, a barn cat colony like that can actually wipe out their own food source. If somebody isn't feeding them, they can actually decimate, like they can clear a square mile of rodents. It's possible. It's difficult, but it can happen. So typically we don't see this go on for any length of time. We see short periods of J-curve growth and then boom. The one example, the other classic example, and this is not in nature, bacteria. So you remember looking at Petri dishes full of bacteria when we were talking about resistant bacteria? When I used to do water quality sampling, we'd take water out of Mill Creek or Yellow Creek and we would sample it, put it in a Petri dish and culture it in a little incubator. And you would let it grow for 48 hours, and you'd see spots where the bacteria were. And then you'd take it out, you'd dump bleach on the whole thing, kill everything, and throw them away. Count your colonies. If you had let that continue to grow until the entire surface of the dish was covered with bacteria, think about that mega plate they made where the whole surface was covered with bacteria, what would happen? What would happen? They'd all die. They're belching out their own wastes. Bacteria emit waste too. They have cellular waste. I mean, it's not feces, it's not urine like we think of waste, but they have bodily wastes. They would kick out those bodily wastes, they'd eat the entire food source, and they would die. Again, it's not a natural environment, it's an artificial environment we've created, and that sort of growth can only be sustained for so long before we have a crash. Important to keep in mind. Now, you know we've got more dance moves coming. Okay, so this is the second growth model we're going to talk about today. And this is going to set you up for seeing rat attack tomorrow. So the logistic growth model. This talks about a population that does something a little bit different. It does J-curve growth for a while, but then instead of crashing, what starts to happen to the slope of that line? It decreases and it decreases until that all flattens out. Remember we said we're looking for the word assumes? The assumption of logistic growth is that as that population gets bigger, births slow down and deaths increase until you get to a point where they pretty much balance out and we have this sort of stable population at some point. That stable population size is what we call carrying capacity. It's how many individuals the environment can support over the long term. You know, in the case of Sally's mouse-pocalypse, birth rates weren't going to decrease, death rates weren't going to increase because she kept providing additional resources. But that doesn't happen in nature. And this is very often called S-curve growth. You have to have a little bit of imagination to see the S in there. But it's kind of an S. It starts off like a J and then it tapers off. And you have these fluctuations around that carrying capacity. So in the logistical growth model, we introduced this idea of limiting factors, and those are things that limit the size of the population. Lack of food, lack of shelter, lack of habitat in some way. The thing that the logistic model assumes, because remember we said every model has its assumptions. Logistic model assumes that carrying capacity isn't going to change. It assumes that carrying capacity does not change. And this is one that we actually see pretty commonly. You're going to do it's kind of like a web activity looking at a population of lions, and you can measure population over the years. And what you see looks an awful lot like that. And it starts to fluctuate, and some years are a little bit higher and some years are a little bit lower. But basically what we've got is a carrying capacity. We've got a number of individuals that the environment can sustainably support over the long term. So, are you ready to do this? The logistical growth model dance?